When developing contracts for the Ethereum virtual machine, you generally break up the project into several contracts for convenience only. In some cases, it is possible to implement all the functionality in one contract. And even where contract splitting was necessary, for example, liquidity pairs in the automated market maker, this didn't lead to any special difficulties. In Ton, it is strongly recommended to avoid unbounded data structures and split a single logical contract into small pieces, each of which manages a small amount of data. The basic example is the implementation of Ton Jetons. This is Ton's version of Ethereum ERC20 token standard. Briefly, we have one Jeton minter contract that stores total supply, minter address, and a couple of references, token description, and Jeton wallet code, and a lot of Jeton wallet contracts, one for each owner of these Jetons. Each such wallet stores only the owner's address, their balance, and Jeton minter address. This is necessary so that the transfer of Jetons occurs directly between wallets and doesn't affect any high-load addresses, which is fundamental for the parallel processing of transactions. That is, get ready so that your contract turns into a group of contracts, and they will actively interact with each other. What follows from this? A new, unique property appears in the logic of your contract: partial execution of transactions. For example, consider the message flow of a standard Ton Jeton. Look at the picture. Here is the Ton Jeton message flow. What follows from the diagram? Sender sends a transfer message to its wallet, sender wallet, and sender wallet reduces the token balance. Sender wallet sends an internal transfer message to the recipient's wallet. Destination wallet increases its token balance. Destination wallet sends transfer notification to its owner. And destination wallet returns excess gas with excesses message on response destination. Actually, that is usually a sender. Note that if the destination wallet was unable to process the internal transfer message, an exception occurred or gas ran out, then this part and subsequent steps will not be executed. But the first step, reducing the balance in sender wallet, will be completed. The result is a partial execution of the transaction, an inconsistent state of the Jeton, and in this case, the loss of money. In the worst case scenario, all the tokens can be stolen in this way. Imagine that you first accrue bonuses to the user and then send the burn message to their Jeton wallet, but you cannot guarantee that the burn will be processed successfully. Even in a single contract like Ton Jeton, there are already quite a few messages, senders, receivers, and pieces of data contained in messages. Now imagine how it looks when you're developing something a little bit more complex, like a decentralized exchange, where the number of messages in one workflow can exceed 10. At Certic, we use the dot language to describe and update such diagrams during the course of the audit. And that's what we recommend to the developers as well. Unlike in Ethereum smart contracts, where the external call must execute before the execution continues, in Ton, the external call is just a message that will be delivered and processed after some time in some new conditions. That requires much more attention from the developer. Using the message flow, first define the entry point. This is the message that starts the cascade of messages in your group of contracts, consequences. It is here that everything needs to be checked: payload, gas supply, etc., in order to minimize the possibility of failure in subsequent stages. If you are not sure whether it will be possible to fulfill all your plans, for example, whether the user has enough tokens to complete the deal, it means that the message flow is probably built incorrectly. In subsequent messages, consequences, all throw statements will play the role of asserts rather than actually checking something. Many contracts also process bounced messages just in case. For example, in Ton Jeton, if the recipient's wallet cannot accept the tokens, it depends on the logic of receiving, then the sender's wallet will process the bounced message and return the tokens to its own balance. In general, we recommend processing bounced messages. However, they can't be used as a means of full protection from failed message processing and incomplete execution. Firstly, it takes gas to send a bounced message and process it. And if there isn't enough provided by the sender, then no bounced. And secondly, Ton does not provide for a chain of jumps. This means a bounced message can't be rebounced. For example, if the destination can't process transfer notification, then the sender wallet can't find this out via bounced messages. A message cascade can be processed over many blocks. Assume that while one message flow is running, an attacker can initiate a second one in parallel. That is, if a property was checked at the beginning, for example, whether the user has enough tokens, do not assume that at the third stage in the same contract they will still satisfy this property. We came up to the most important advice. Use carry value pattern. In Ton Jeton this is demonstrated. Sender wallet subtracts the balance and sends it with internal transfer message to destination wallet. And it, in turn, receives the balance with the message and adds it to its own balance, or bounces it back. The value is transferred, not the message. You have probably already noticed that Jeton implementation doesn't allow you finding out your Jeton balance on chain. That is because such a question doesn't fit the pattern. By the time the response to the getBalance message reaches the requester, this balance could already have been spent by someone. Let's implement an alternative. At this picture, you can see that master sends a message provide balance to the wallet. Wallet zeroes its balance and sends back take balance message. Master receives the money, decides if it has enough and either uses it, debits something in return, or sends it back to wallet. So that is somewhat like getting the balance. From carry value pattern, it follows that your group of contracts will often receive not just a request, but a request along with a value. So you can't just refuse to execute the request via throw statement. You have to send the jetons back to the sender. For example, a typical flow start. Sender sends an transfer message via sender wallet to your contract wallet, specifying forward Ton amount and forward payload for your contract. Sender wallet sends an internal transfer message to your contract wallet. Your contract wallet sends a transfer notification message to your contract, delivering forward Ton amount, forward payload, and sender address and Jeton amount. And here, in your contract, in handle transfer message, the flow begins. There, you need to figure out what kind of request it was, whether there is enough gas to complete it, and whether everything is correct in the payload. At this stage, you should not use throw statement, because then the jetons will be simply lost and the request will not be executed. It's worth using the try-catch statements. If something doesn't meet the expectations of your contract, the jetons must be returned. But be careful. Send returning transfer to sender address, not to any real Jeton wallets. You don't know if you got the transfer notification from a real wallet or someone is joking. If your contract receives unexpected or unknown jetons, they must also be returned. So, to summarize, Ton requires much more design efforts from the developer to avoid unbounded data structures and to allow infinite sharding paradigm. Even with the correct design and using the carry value pattern, the Ton developer has to take into account the async nature of the tone messages. Accepting the JET requires manual, careful payload analysis and checking the conditions. Return the value via sender address since messages can be forged.